How to describe steady state photoluminescence and time resolved photoluminescence in a research paper. These two characterization techniques must support each other. This is the steady state photoluminescence graph, where on x-axis we have the wavelength here, and the y-axis we have the PL intensity. While in time resolved photoluminescence graph, on x-axis we have the decay time here in nanosecond and microsecond, and the y-axis we have intensity. So let's get started. So look at this steady state photoluminescence graph. Here we have three samples. This is the perovskite, and here we have another sample, and here we have another sample. So we have three curve, three PL intensity. So we can see that for the pristine structure, the peak is very low here. We can hardly see the peak here. This means that in this material, there are a lot of defects. So this means the excited electron basically lost. And those electrons basically lost because of non-radiative recombination. This is very, very important. Non-radiative recombination means that, for example, when electron jump from the valence band to the conduction band, so in the conduction band or in the higher states, there are many defects there. So electron basically lost in those defects. So electron recombine there, but there is no emission of photons. Electron loss because of the heat or phonon, etc. So this is why it is called non-radiative. There is no radiation in this recombination, and that is detrimental for the device. So we do not want that in or R. So here basically in this pristine structure, basically there are a lot of defects. So the peak is very low here. What happened when we add this material into the perovskite film? So this means that the peak intensity increases. So it gives us the message that the defects decreases in this sample here. The defects start getting decreases. Now what happened when we add another material to the perovskite in the form of thin film, in the form of solution, in the form of precursor, doping, etc. So we can see that there is a significant increase in the PL intensity. So it gives us a clear message that the defects decreases significantly or almost finished. This is because of this highest peak intensity. So this is how we have to write about these details in the research paper. Now there is another phenomena. What phenomena we can observe here? That the peak is basically shifting from the pristine toward the lower wavelength, and that is basically we call blue shift here. Blue shift means that when the shift is toward the lower wavelength, and we know that there is a relation that important here, that hc divided by lambda. So when the wavelength is decreasing, so the band gap is increasing. So from the top plot we can derive that this, when the defects decreases in the film, so in that case we have the larger band gap here. The band gap increases here. So this kind of information we have to write about this graph here. So we can see here that this figure XX shows the steady state PL of the perovskite film. Among these three, the last one is the strongest peak here. Yeah, peak here, and it's revealing that they suppress the non-radiative recombination. And you can also write here that they because of this passivation or addition, they basically reduce the defects. It's the same thing here. You can write they improve the crystallinity of the material, etc. In addition, there is a blue shift here of the emission peak, suggests that broadening the band gap of the lattice, the third one here. You see? Yeah. This is how. So from the top plot we can confirm, and here we confirm that for the first two we have the same band gap here, while the last one we get increased band gap. Yes. Now let's come to the time resolved photoluminescence. Very important here. So we can see here we have the same three sample here with the same color. This is the pristine one, this is the second one here, and this is the third one here. And those are the original data here, and we have the fitted line here. This is basically the fitted model. These are the model here. So by exponential model here we use here. They use the other use basically by exponential model, and from I will explain these models in a separate videos. There is also a single exponential model here. but this is the by exponential, and these are two times here, the time 1, the time 2 here. These are basically the lifetime for the charge carrier. So one we have called fast decay and another we call slower decay, and they basically represent two different phenomena in the material sense here. Yes, so clearly I can say that this one has the longest average lifetime. How? I explain from my terminology here like this. For example, if I draw a line here, so at this point here on the x-axis we have the time here. So the same line up take, so you see the time, the lifetime increases for these, for the same intensity here. So we can clearly see that this last sample have the longest lifetime here. Yeah, the time resolved photoluminescence fitted result shows that the average lifetime for this is this, for the second one is exhibited this, while this one treated displayed the longest average lifetime. This is how we describe the steady state photoluminescence and time resolved photoluminescence, and these graphs support each other. I took this data from the important paper. This is the paper here. These are the graphs I took from the paper, and this paper is published in Nature Communication with title this by UG Lu in 2023 under the lessons 4.0 Creative Commons, and this is the link to the license.